All right, so we're looking at number 12 here about frames of reference and relative velocity. And we're given these four cars. Told lots of stuff about them. And then we're asked, they also tell us about another car. And they ask us all sorts of questions. But let's see how we would set this up. All right. So the people who is doing this one with me? Who is interested in us doing this one? Nobody? Okay, just one person. All right. So which parts did you want to do with? Or start off with? There's so many of them that we could pick one and do.
Part A, start off with.
Start with part A? Okay. Well, I think A you can kind of answer on your own, to be honest. What frame of reference do you think those measurements are from? What do you think? What is our kind of default frame of reference? So why don't we do part B? Okay. So for part B, the question asks, what's the velocity of car A with respect to car B? All right, I'm going to put some data over here just so I have it. And I know the velocity of car A compared to the Earth. I'm not going to call it Earth. I'm going to call it the ground. And I know the velocity of B to the ground. I know the velocity of C to the ground. I know the velocity of D to the ground. I think I do. On our figure, which direction does the class want to call positive? Well, there's two directions in our diagram. There's right and there's left. Which one do you want to call positive, right or left?
Right.
To the right? Okay. So we'll take to the right as positive. That means A is positive 12 meters per second. A to the ground. B to the ground is 0. C to the ground is negative 15. D to the ground is negative 20. And then I'm going to look at my equation sheet for my valid physics equations, which are these under relative motion here. And I'm just going to transcribe those so I have them right here. This is exactly what I would be looking for if you were being evaluated on this problem solving. Oops. Make that clearer. I'll move this over. All right. That's kind of all my given information. And we said we were going to do B, right? Part B. So part B wants the velocity of A with respect to B, I think it said, right? Yep. They use that little slash. I don't really like that. So what I need to set up is my equation, something that adds up to that. And it would have A compared to something plus that same something compared to B. And, well, the only thing I know like A compared to is the ground right now. So I would do A to the ground plus the velocity of G of the ground to B. And what I can do is now substitute in here. I know that's positive 12 meters per second. And I don't know the ground to car B, but I do know B to the ground is 0. So ground to B is just the opposite of 0. Or I switched the direction of it. So that would be 0. So this would be my final answer. Velocity of AB equals positive 12 meters per second. Is there another part of this problem anyone wants to see?
Velocity B to A.
Well, since you know the velocity of A to B, you know the velocity of B to A is reversing.
Just the opposite, okay.
Yeah. Probably the center term is going to end up being your ground a lot of times. It might be the easiest thing.
Okay.
I think it's one of the last parts, part H, where they introduce a car E, okay? And it tells you, like, the Audi and the Edsel are moving at 8 meters per second from the frame of reference of, so from the point of view of, why don't we do part H?
Yeah.
Okay? Because that was a little trickier. Did you notice that there were hints available?
Yeah.
Okay. So from the point of view of the driver of the Audi, the Edsel is moving at 8 meters per second. But they don't tell us what direction, do they?
No.
Oh, okay. They're messing with us now. So this will be part H. And the new fact that they give us is the velocity of the Edsel with respect to A is either plus 8 or minus 8 meters per second. I think that's what they say, right? Yeah. So I think we'll have to end up doing it twice. Once where we put in positive 8, and once where we put in negative 8. Okay? I'm using the same equations. And what do they actually want to know? What is the speed of the Edsel relative to D? All right, so they want to know E with respect to D. So they want to know the velocity of E with respect to D. And that would have to be the velocity of E with respect to something plus the velocity of something, that same something with respect to D. I don't know E to the ground, but I do know I could figure out very easily the ground to D.
Yeah.
Okay? So let's put ground in here. But to do this, to be able to put it into there, this is where, unfortunately, I've got to figure out what is the E to the ground to be able to substitute in there.
Yeah.
So that would be E to something plus something to the ground. Oh, I know E to A.
Yeah.
And I know A to the ground. That makes sense? So I can put in here E to A if it's plus 8 meters per second plus A to the ground. What was A to the ground?
12 meters per second, positive.
So plus 12 meters per second. That would equal positive 20 meters per second. But if it's negative 8 meters per second, that plus 12 meters per second gives only plus 4 meters per second.
How how do you determine like which one to plug in?
Well, for right now, I have to go with both. So we're going to have to do it twice again. So if I use e to the ground as plus 20, I'm going to move plus 20 plus, now d to the ground is negative 20, so the ground to d is plus 20, positive 20 meters per second. So if I use this one, I get 40, positive 40 meters per second. If I use the other one, which is what, 4? I get positive 24 meters per second. So it could be either one of those, and luckily I have a choice that says 24 or 40. All right, we're looking at number 3. We've got a storm near these islands, spilled 29,000 rubber ducks and other bath toys. 10 months later, hundreds of rubber ducks began disappearing along shoreline near Alaska, roughly 2,600 kilometers away. Approximate speed in meters per second of the ocean currents that carried the ducks to shore. Use an average month of length 30 days. So we could solve this in the length and time units they've given us in the problem, kilometers and months, and then convert kilometers per month to meters per second. Or, before we get started, we could convert kilometers to meters and months to seconds. Which way would the class prefer?
I think you should convert first.
Convert first, get everything into standard meters and seconds, and then work. That's a good idea. I like that idea. So I need to take 2,600 kilometers and get it to equal something in meters. Whenever I'm doing conversions, like you learned in chemistry, I think of the number 1 and multiplying by it. So I put what I want to get rid of opposite where I have it, and opposite that. So there, in 1 kilometer, there's 1,000 meters. That means 2,600 kilometers would end up being 2.6 times 10 to the 6th meters. Or 26 followed by 5 zeros is the other way to think about it. So you can think about it if you don't like scientific notation. Either way, they're both the same. And then I want to do 3 months? 10 months. 10 months, and I want to end up with seconds over here, so I need to go month to day, for me day to hour, and then I'm going to go hour to second and end up with some number in seconds.
I'm going to go hours to minutes.
Could, but I'm just going to do it in one big step, because I know just off the top of my head that there's 3,600 seconds in an hour. And in one day there's 24 hours. So it depends on the facts you have at your fingertips.
Oh.
And in 1 month, there's 30 days. Because that's what they told me, use an approximate month of 30 days. I can come and see you individually. I'll be more than happy to. Alright, so let's see. 10 times 30 times 24 times 3600. Oh, it's all ones on the bottom, so dividing by the bottom is easy. So I think I need to move everything over. Also, I move with me. I get 2, 5, 9, 2, 1, 2, 3, 4 seconds. Or I can write that as 2.592 times 10 to the 1, 2, 3, 4, 5, 6, 7, 7. What a horrible 7. Okay. Alright, so now I'm ready to actually do some physics. Alright, now I have my unit conversions done. And I think we mentioned in the preliminary that we would use the definition of speed, which is distance over time. So I'm going to write that equation. So speed equals distance over time. Kind of like the basic version of our definition of velocity. And so I know my distance, 2.6 times 10 to the 6th meters. And I know my time, 2.592 times 10 to the 7th seconds. And now, nicely, I just stored those in my calculator, so I don't even have to put them in. Actually, I didn't. Whoops. 2.6 divided by. And I got 0.100 meters per second. So about 10 centimeters a second. Yeah. Easy to happen when we're doing some. How are we on number 3? Good? Alright, so number 6, we've got the golfer putts and 4.8 meters from the hole straight, and then overshoots by 1.5. The golf puts it back and sinks the putt for par. And I know it's about distance and displacement. So I'm going to draw myself a little diagram. Here's where the ball starts. There's the cup. So the ball goes here and keeps going, turns around, and comes back to here. And I know this is 4.8 meters. And this is 1.5 meters, I think, for me. Yeah. And I hate it when I do that. And which way do we want to call positive? I'm going to suggest to the right, because I think probably the person who wrote the problem was thinking towards the hole on the initial putt would be positive. So, all right, let's grab our equations for distance and displacement, which are the two down here. And so for part A, they want to know distance, right? Yep. So for part A, I'm going to use the distance. Whoops, wrong sheet. Distance equals d1 plus d2 plus d3 plus dot 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 dot. How many position measurements do I have here in the path, in the whole path? 3? Do you guys agree? Okay. So the distance is going to be the first distance it covers, which is 4.8 meters, plus the next distance it covers, 1.5 meters, plus the last distance it covers, 1.5 meters, giving me 7.8 meters. Did a little math in my head. Stop me if you have questions. For part B, they want displacement. And displacement, we remember from our equation sheet, is final position minus initial position. So, let's call this initial position 0. Is everyone okay with that? Okay. So our displacement, our final position is going to be positive 4.8 meters. Our initial position is 0, so our displacement is positive 4.8 meters.